Good morning, good afternoon. Thank you for joining us today. Excited to have you for our first inaugural Let's Talk Tokens, a new AMA series we're launching with AI experts, both from Predibase, and we'll bring some in the future from elsewhere. This one, though, is focused on reinforcement fine-tuning and GRPO, drawing on experiences we have building the leading course for deep learning AI and also building a product and working with customers, deploying cool use cases and building our own use cases. The AMA is meant to be an intimate session, so we kept it small on purpose so we could answer your questions, make sure it's highly interactive, and fun, in an environment where you can anything goes. So any questions you have on RFT, we'll cover. Let's go to the next slide here. I'm Michael Ortega, I lead marketing here at Predibase. I got our three RFT experts, and really are beyond that. Their experience extends far beyond that, but I'm joined by Arnav, Ajinkya, and Travis. Travis is our CTO co-founder, leads the development of product and our roadmap here and strategy here at Predibase. Also, the author of Lorax, the multi-LoRa open source serving package that we've invented, which is pretty awesome as well. And Ajinkya and Arnav are on our ML engineering team. Arnav as an engineering lead and Ajinkya as a senior research engineer. Both were intimately involved in development of RFT solution. Arnav and Travis led the deep learning AI course we did on RFT and GRPO, but also have built, as I mentioned, use cases and work with customers. So lots of best practices, training our own models, helping others train models. We'll share all the landmines we've stepped on. But yeah, excited to have everyone here. We're based in San Francisco. Please let us know in chat where you're from. Would love to hear. And let's keep going along and get this started. Next slide, Arnav. Yeah, so just real briefly before we jump in, just a quick reminder. The lines are muted, but this is meant to be an interactive session. So please jump in chat. Let us know where you're from. We also have a poll here to help us when we do future sessions, create content that you want, get the right experts in the room. So please let us take a minute to do the poll, help us steer the direction of our next session. This will be recorded as well and shared after. And please do put your questions either in the QA or chat as we get going here. And with that, I think I'm going to head it over to Arnav, who's going to do a quick primer to make sure everyone's up to speed on RFT and GRPO, and then we're going to jump into your questions.
Cool. Thanks, Michael. And yeah, excited to meet everyone today. So yeah, essentially over the next 10 minutes, we'll do a quick intro of GRPO RFT, sort of where it fits in the picture and why you should care about it now. Hopefully, some of you attended the Deep Learning AI course or read about GRPO or read through the DeepSeek paper. So this should all be very familiar. But yeah, so essentially, these days, there's many ways to customize your models. Some people go down the path of general prompt engineering. Others do more complex things like drag, and then combine these in agentic workflows. And sort of a separate direction that emerged also, has been around for a long time, but has been gaining a lot of traction, is fine-tuning small language models. And so if you haven't fine-tuned one before, the good news is that supervised fine-tuning works. And so when you take a general purpose model and you fine-tune it on real task-specific data, like one of our customers, Conversa, did, the gains are, you see gains across the board: lower cost, higher quality, better throughput. And we see this across a variety of use cases with our customers. So, another customer upstates fine-tuned this model called Solar Proofread, and that doesn't just match GPT-4o performance, but beats it, even after fine-tuning GPT-4o mini. And what's really fascinating about this is that, it works really, really well. We've seen this time and time again, but it comes with quite a high cost. You need, and in particular, you need clean, curated, labeled data sets and quite a lot of it. And for many organizations, this actually is not so feasible. And it's not just the upfront effort of curating such a data set, but then there's a cost of refining it or maintaining it and continuously curating it to improve your models and driving performance improvements. So, what can we do about this if fine-tuning is very promising? And that sort of brings us to the topic today, which is reinforcement fine-tuning and its promise. And if you worked in machine learning, the things I described in the last two slides are not new or shouldn't be a surprise. Most of the time, or 90% of your job is about labeling data, and the other 10% is usually venting about it. But And supervised fine-tuning, the truth is that the reason we put in this effort is that supervised fine-tuning is powerful, but it's expensive, slow, hard to scale. And what's really fascinating about reinforcement fine-tuning is that it gives us a way to tune these models without hand labeling every single example. And instead of curating these large data sets, what you're looking for, what you're really doing is defining what good behavior looks like and then letting the model learn from feedback on its own. And that's the RFT promise. Less labeling, less complaining, and still better models. And why should you care about this now? Like, why today? Why not 2 years ago? Well, earlier this year, the DeepSeek team announced DeepSeek R1, which kind of became all the rage. And it was one of the first major models to show a new promising direction in reinforcement learning and reinforcement learning based fine tuning. And until this point, most teams like OpenAI or Anthropic use reinforcement learning with human feedback, also called RLHF. And it's sort of the method that drove improvement in GPT 3.5 and the GPT-4 series of models. But RLHF in general is very expensive because it requires collecting a lot of human data for alignment, which, they work with many companies to do so and also their own labeling mechanisms. And then training these models requires this algorithmic sort of a scheme called PPO. And it's pretty computationally expensive and unstable. And why we care about this now is that DeepSeek, one of the most interesting things is that they introduced this new algorithm called GRPO, which is a variant of PPO and DPO. And GRPO stands for Group Relative Policy Optimization. And it actually makes reinforcement learning much more intuitive, much easier to both implement and then scale to your tasks. And the results sort of speak for themselves, right? Across math, if you look at these benchmarks, across math, reasoning, coding, SWE-bench, DeepSeek R1 kind of holds its own against OpenAI's O1 or O3 models and other top tier baselines. And so RFT isn't just like sort of promising in theory, it's sort of like actually delivering in practice. And so what is GRPO? Well, this diagram is kind of complicated, but the long story short is that it is sort of the driving factor behind DeepSeek R1 and a variant of the PPO algorithm. And it simplifies reinforcement fine-tuning in two ways. It, one, removes the value model that's a big part of the PPO training loop. And the second is that it estimates rewards using a group of responses. And so it's not just easier to implement and creates like a more efficient training loop, but it also unlocks a more flexible training loop. Now, in things like RLHF or DPO, where you have these preference-based reward models, well, not in DPO, but GRPO lets you define the way GRPO works and why it's so powerful is that it lets you define these programmatic reward functions, which gives you full control over the behaviors you want the model to learn. And that's really powerful for things like code generation, math, and multi-step reasoning, where you're not just looking for, is this response better than this response or more preferred, but you can teach the model or tell it, hey, you went wrong here or you went right here. So do more of this and do less of this. And so it's all about these objective outcomes that you can encode sort of as domain knowledge into the training process. And so that's why it's been very exciting. We've seen a lot of very interesting use cases sort of emerge. A lot of customers see early success. Deep research and all of these models are sort of based on the fundamental like ideas behind reinforcement learning. And in case you're curious about when you should actually use RFT, broadly, there's like 3 buckets, right? One is if you don't have label data, which many organizations don't, either because it's expensive or it's difficult to collect for the task. But if you can verify the correctness of the output, then that's a great reason to use RFT. And a good example of this is transpiling code from one source language to one target language, where you know that the code either works correctly because of test cases, even if you don't know the exact output. The second is when you have limited label data. So there's some, but it's not enough for supervised fine-tuning, or you're not seeing big improvements when you do supervised fine-tuning. So generally less than 100 labeled examples, but it depends on the task. And the third is when chain of thought style prompting improves performance. So instead of zero shot inference or zero shot with chain of like just zero shot or regular prompting, when you do infuse chain of thought or chain of thought with K-shot, and you see big lifts compared to the base model performance, it's a really good sign that a process like reinforcement fine-tuning will help improve performance even further. And what are some good use cases or tasks suited for RFT? For those unfamiliar, well, one is mathematical problem solving. This is sort of like a bucket, but the bigger bucket is sort of like problem solving in general. So anywhere where the models can sort of walk you through their thought process, show you their work, and provide detailed reasoning as they work towards an answer is a great example of RFT. So you can think of things like agentic workflows, where you have multi-steps with reasoning before doing actions. Perfect example for RFT. Code generation, debugging, big. There's a lot of companies doing a lot of work here. Everything from like Cursor to all these other coding platforms are deeply integrated in this loop of is the user editing the stuff, or are they writing new test cases, and then using reinforcement learning to improve their models. And the third is sort of logical and multi-step reasoning, which I sort of alluded to before, but anywhere where you need to think more deeply and refine your logic. So games that require reasoning and strategy, to tasks that require reasoning and strategy, such as solving math proofs or agent planning, stuff like that also fits in really well. And just to give you sort of a high level idea of what the architecture itself looks like to do something like this, you need a way to connect your data set from where it lives, have your trainer and training loop, and then be able to send checkpoints to do this like online training process where you use the checkpoint from every step to generate data for the next step and sort of loop it back. Calculate some rewards, which are done through your reward functions, and then update your weights. There are open implementations such as in TRL, and then we've also innovated on top of that by adding a lot of new features, both in terms of like improving training times, training speed, reliability, and observability around this process, because it can be pretty complex. And so, we spent a lot of time doing it and encoding like some of the best practices that we've seen from our own experiments and working with early adopters and customers. That's sort of like the high level overview. There are obviously many sub steps that maybe you guys have questions on that we can maybe start answering now. So Michael, this will be a good point for me to hand it back to you, and maybe we can get into Q&A.
Yeah, absolutely. So some questions coming in Q&A as well as chat. I saw Johnny asked, do we have documentation about our RFT approach? We definitely do in our docs. We can post that link here shortly. And I think you briefly talked about our approach, Arnav. I don't know I guess, is there anything else you'd want to mention about our framework or approach?
Yeah, there's three things I'd like to mention, I think, if I calculate that right. So the first is that there's GRPO, and then we're sort of calling it RFT because there are some things that we've learned through our own experiences about the best way to maximize our GRPO performance. And one of those steps, for example, is this process called SFT warmup, where you essentially sort of like bootstrap the process of getting good performance by showing it examples of what are good ahead of time. And those can be dynamically generated as well from reward functions. And I'm happy to talk about that more if there's like more questions on it. But the thing I wanted to abstract away from is that the way we built the product in general is that you can connect these pieces together in a pretty seamless way. So train SFT, then point at that and say, now do GRPO, and it would all just work pretty seamlessly. So that's one. The second is, I think the way a lot of people have thought about reward functions is that, they need to be static and fixed throughout the course of training. But what we've learned from our experience is that, debugging them can be often a bit tricky, and also learning can saturate during the training process because all the completions start getting the same rewards. So we have a way to dynamically update reward functions during the course of training, which means that you can experiment or provide more fine-grained rewards so that you can help push the model towards better and better performance without having to stop, start, restart runs, change things. And the third is, I think observability is probably one of the most key insights that we've had from our own experiments. understanding where things are going wrong in the rewards, understanding where things are going wrong as the model is generating, where it's struggling. And we've built these observability tools directly into the training process. And it makes it very easy to quickly figure out where the model is struggling, how to fix it, and also where is it showing gains. And you can compare this, sort of over time. So a lot of this is covered in our docs, but I think yeah, those three buckets of things I'd say are pretty unique to the way we've thought about RFT. And it's all grounded in sort of like the practitioner-led battle, like our own experiences doing this over the last 6 months. And yeah, Travis, Ajinkya, I don't know if there's anything else you'd like to add.
Great. So getting some questions in the Q&A as well. Maybe the first one, Ajinkya maybe want to take it is, we think about, you talked a little about like the use cases and SFT and RFT. Are there like early indicators or signals that might let you know that RFT would be a good solution for your problem or might beat, SFT for a specific task or things you look for, Ajinkya, having trained some of these models?
Yeah, I think like one quick check that you can do is if you do chain of thought reasoning that say that think more or reason step by step, add this thing in your prompt and let the model take some time to reason through the solution before arriving at the solution. And then that somehow improves the model performance, then that's a great indicator that RFT should help in this case. And as Arnav mentioned earlier, anything that requires multiple reasoning steps, it requires you to think through things, are a great fit for RFT. Unlike other cases where it's just classification, given this statement, classify this as positive or negative, sentiment analysis, right? So classification-based use cases are great for SFT, but anything that requires complex output and reasoning is a great fit for GRPO and RL in general.
Great. And maybe like for you and Travis as well, like you kind of mentioned like classification use cases do really well for SFT. We have a lot of experience there too. Are there certain use cases where RFT, right off the bat, or reasoning isn't ideal and SFT is like a great solution? Either Travis or Ajinkya, if you have
Yeah,
thoughts.
yeah. So I mean, I think there are certainly cases where RFT is overkill. I mean, it's worth mentioning that RFT is more expensive than SFT, which is true, right? So if you're thinking about like how to be the most efficient with the resources that you have, the money that you have, like if you have like a fixed spending budget for training, and you have tons and tons of label data, SFT is definitely going to be more economical. It's going to give you more performance for the every dollar that you spend in those cases. So that's where I'd say SFT tends to do the best is when like having a good amount of ground truth label data is not a big concern. RFT, definitely as Ajinkya said, is really well suited to chain of thought reasoning problems. The biggest issue there is that sourcing good reasoning data is very hard. I mean, you can do it through distillation, but if you want to do better than what existing models can do because your task is very domain specific, you kind of have no choice but to do something like RFT, right? Because you just don't have ground truth. Similarly, in the case of some code generation problems, you might not have ground truth, and so RFT could be valuable. But even in the case of some classification problems, RFT could be useful if it's, one where you have very sparse data. Maybe you don't have a lot of labels for specific classes. I think in some cases I've seen like papers that are using RFT for classification, like the biology or chemistry domains, right? Where it's like very difficult, kind of like non-obvious, why certain inputs lead to certain outputs. So there's definitely cases even outside of like reasoning where it can be very useful, but definitely the trade-off there is like on the kind of per step, per sample efficiency. That's where, RFT is more expensive than SFT, and then that's where that needs to be taken into account.
Great. And I know you're talking a little bit about, we talked about data and sort of what access you have to, enough label data, that sort of thing. Someone asked in chat here, I don't know if you know specifically for an NLP to SQL use case, but someone would say, hey, what's the minimal data set size for an NLP to SQL GRPO pipeline? I don't know if we have any thoughts on that based on our experiments.
I can quickly talk a little bit about that. So for one of the use cases, we have seen good results with as few as 10 samples. So we had a use case for text to code generation, and with a bigger model and better context, better prompts and everything, we were able to beat a bigger flagship model like GPT-4o Mini with a smaller model. So even 10 samples, like RFT is extremely sample efficient, as Travis was saying earlier. So even with 10 samples, you can go a lot.
Yeah,
And go ahead. Yeah, please.
so yeah, I think like the general formula for RFT is start with few examples, but make sure like you can learn on it. So you know the reward function of pushing the model in the right direction. And then as you scale up the number of prompts, it's less about scaling the number, but more about scaling the diversity of types of prompts and challenges you want the model to solve so it can find those efficient strategies. And I think across like many like papers these days, like that's sort of like the two-level approach that people take. But yeah, text to SQL we've seen as good as 10. I think we also did like natural language to ORL. The code translation, Travis, how many did we use? Like 100?
We had initial tests with around 10 to 20, and then I think our final version had about 100 examples. So.
Yeah. And we got like state-of-the-art models through that. So usually not a whole lot of data, but it needs to be high quality.
Yeah, and I think one thing to point out here is that the reason why this is the case is that SFT has this problem of, this overfitting problem of like essentially memorizing examples, because RL is never really given, or RFT specifically is never really given the exact kind of like input-output pair that it needs to learn from. It's just given signal and whether or not it's directionally going in the right direction. It tends to be a lot less susceptible to this kind of overfitting problem. And that's one of the reasons why you can get away with training with just 10 examples in some cases and still get like significant lifts in performance.
Nice. And there was a second part of that question. It's already asking about how to correlate with other hyperparameters. I don't know if you have thoughts on that as well. And they said like example group size.
Yeah. I think like there's some are, well, I guess model size is not a hyperparameter, but I'm going to count it as one. And Ajinkya, feel free to chime in here. Travis, you too. I think the ones that we've seen in general are model size is not like a hyperparameter, but larger models do better for RFT. They have more reasoning power from more pre-training, which helps a lot. Scaling up the number of generations, so I guess here you're calling group size, does have a big effect. Especially for tasks where the model starts off with very poor performance. So you can imagine in cases where if you only have 8 generations, but they're all the same rewards, then the model doesn't really learn anything. But when you scale up the number of generations, the odds of getting at least some unique answers that have non-zero and not the same as others like increases. And so that helps bootstrap the learning process. But obviously there's a trade-off of cost because it's expensive to do more generations, both in terms of, just training time. And then third is, I think, well, this is task dependent, but number of output tokens. For some problems where the model already has a good understanding of the task, but it needs to just improve it, you can get away with a fairly short set of output token lengths. Right. But in cases where like the model doesn't have the deepest of understandings about the problem, or like the initial scores on your reward functions are lower, generally the trend I've seen is that the model actually increases its reasoning context length during the course of training. And so there, once again, you want to kind of increase the output token budget to give it the room to do like longer generations during training. And then maybe the last one, it's not a hyperparameter, but it's more like a big factor that affects things, which is prompt size. The interesting thing about RFT is that it's like all the work you've done for prompt engineering doesn't have to like go away. In fact, it's very useful as a starting point for RFT. And the reason I say that is a lot of the more context you can kind of give it in the prompts, that makes it easy. The better it is for the model because it makes it easier to get non-zero sort of scores on your reward functions, and that also helps boost performance a lot. At least like we've consistently seen that larger models, larger context lengths, both input and output make material difference to performance. Yeah, Ajinkya, I don't know if, or Travis, you guys have seen other things.
Yeah, I think just one comment on group size. I think the most important thing when you're doing GRPO is to have a diversity of different reward scores that come out of any particular step. And so that can either be achieved by having a fewer number of generations slash a smaller group size, but having very fine-grained reward functions where every single output is going to get like a very meaningfully different score. Or if that's too difficult, or if like you're, like getting a positive score on a particular attribute is a very hard thing to do, as Arnav said, scaling up the group size, scaling up the number of generations is a way to compensate for that. So really, it's ultimately a matter of like, are you seeing good variation in your outputs and in your rewards? And if not, then you'll want to increase your group size to kind of compensate for that in most cases. One comment I also want to say is on hyperparameters, one that we've actually seen is not as important as you might think is the beta param for KL divergence. And I suspect the reason why that is because when a lot of people are doing reinforcement learning and reinforcement fine tuning, they're doing it on general models where it's kind of like a post fine tuning step where they're like, okay, I want to align it a little bit more, but I don't want to make it lose any of the, positive behaviors that it had previously. So they impose this KL divergence penalty term to kind of prevent it from forgetting, what it already knows that's not specific to the thing that's you're trying to improve on. But for us and most of the use cases that we do, we're actually trying to steer the model towards doing something very specific, like doing one thing really well. And in those cases, you actually don't want this kind of KL divergence penalty holding you back. You actually want the model to just try to optimize purely for doing whatever it is that you're trying to get it to do in the moment. So that's just one thing to note that's often different between people that are doing RFT for alignment on general models, which is like the labs like OpenAI and so forth, versus people that are trying to train a model to do something very specific like natural language to SQL.
Awesome. And I don't know if you mentioned like model size as a parameter. Is there a sweet spot in your mind for model size between like considering like, performance and efficiency and cost where you get really good performance, but you're not using the biggest model out there?
Yeah, great question, Michael. I think from what we've seen, sort of the 32 billion parameter range models are in the sweet spot, both from like a performance perspective, where they show significantly better learning and end performance compared to like the 8 billion parameter range, which is less true in the case of SFT, where it's more similar. And the other thing about 32 billion parameter models is that you can run them efficiently at inference time on single GPUs with or without like quantization. So both from like the training perspective, you can do it on like single or two GPUs or four GPUs, and then at inference time on a single one. So it balances that cost trade-off pretty well. We've also talked to people and also done some RFT on larger models like 70 billion. If quality is really, really important, then you do have to go upwards in terms of size. But if like getting good quality is important than getting like at least a minimum quality, then I think you can get away with 32 billion. And last thought is we can always do a two-step process, take a large model, do RFT, get really good quality, and then work on distillation into a smaller model. I think it's a bit more complex with reasoning style models like these, but still can be done.
Great. And I see some stuff in chat and Q&A about rewards, and so maybe we'll start transition there. This one is in chat. Are relaxed valuation functions higher scores better or worse than strict ones with lower scores? And does changing the strictness of the valuation rules during the training have noticeable effects during the training? Any thoughts on that? Who wants to take it?
Yeah, I think one comment I'd say is just that So the way that the normalization works in GRPO is that the absolute value of the reward actually doesn't matter, interestingly enough. So it could be like 10 or 100 or 1,000. All that matters really is like the kind of the variation between the different outputs, so the spread. And so that, because that's where you ultimately compute the advantage from. So that's, I think, probably the most important thing to bear in mind is just that, if you kind of want to scale up your reward scores, 10x or 100x, thinking that will kind of like emphasize things more, like that oftentimes doesn't actually work out the way that you expect it to, given how the GRPO kind of math works under the hood. In terms of like the strictness of the valuation function, um, yeah, I think like what we have seen work pretty well in practice in terms of like getting the model to be very strict about adherence to certain criteria is that instead of like, say you have like five different things you care about, like formatting, correctness, whatever other things like speed or something like that. Oftentimes, what people do is they'll try to assess each of these independently. Like, here's a formatting reward function, here's a speed reward function. And then, in one step, the model might get like a 0 reward on formatting and a 1 on speed. And then the next step, it'll get like a 1 on formatting and a 0 on speed. And sometimes what they'll do is then they'll try to scale the scores kind of to this point, like differently to kind of emphasize one more than the other and be like, well, let's give formatting like 0 or 10 and give speed 0 or 1. But because of the reason that I just mentioned, like if you do that, you might actually not make a difference in terms of how the learning process proceeds. So what I've seen people propose instead, I think in some of our tests, we kind of found this to work pretty well also, is that if you really want to focus on being strict about a specific criteria, particularly early on, where it's like, hey, if you don't get this right, nothing else matters. Instead of just scaling up the value, what you can do is you can make all the other rewards conditioned on getting that reward right. So, for example, you could say, formatting reward is 0 or 1, and then all the other rewards like correctness, speed, etc., are just 0 unless formatting is 1. And if you do that, then that kind of enforces that strictness in a way that is compatible with like the overall framework of how GRPO works.
Cool approach. Oh,
Y-
you were gonna say something, Arnav?
Yeah. I was going to add. So one more thing that's pretty interesting about like the second part of this question, also totally agree with everything Travis said, is the changing the strictness of the valuation rules during training have noticeable effects during training. So yes, in general, like this all depends on having, I think in GRPO, it's really important to sort of have a baseline understanding of performance before you even go into doing it. If the model is already, let's say, that you're doing like a classification task with GRPO and you're seeing 30% accuracy, that means it's kind of a hard task. And so what you'll need to do is write reward functions that are less strict, but more directionally like forgiving. So it starts to make directional improvement in the earlier parts of training. But if the scores at the beginning itself are quite high, like 70%, and you're trying to get last mile performance, then you can be much stricter because it already knows how to do well. And you just have to tell it like how to differentiate how to differentiate like the good from the bad when it's already doing well. So you usually will have to be stricter in those scenarios to produce like the spread of scores so that it can learn. And then the other thing is that over the course of training, right, you might go from 30% to 70%, right? And at that point, those reward functions may not be so effective. So at that point, you might want to again make those like the increased strictness of those reward functions. We've seen this work really well in practice from our own experiments, and also why we let you do like dynamic reward functions in the product.
Great. And I know, you and Ajinkya have trained a lot of codegen models, so different logic ones, worked with numerous customers. What is our other either like best practices or maybe your like checklist as you're creating a reward function? How do you think about that and how should people be thinking about it?
Ajinkya, you want to take this one?
Yeah, so the checklist part, right? Like how do you think about the what are the things you need? I guess the most important thing is you need to take your problem and evaluate it once using chain of thought, or like evaluate a model. You evaluate your problem using some model, and during this process you are going to create some evaluation functions, right? That is going to be part of like extracting some stuff from the model's output, then evaluating whether the extracted stuff is matches with the ground truth or not. And so once you have this pipeline set up, and like your goal should be to improve this through prompt tuning and like RAG, let's say, right? So once you get to a level of accuracy that you can't reasonably improve, then you can go and start thinking about RFT, because at this point you have the evaluation functions and you have uh, the prompt and everything else set up, right? So then going from there to RFT is a pretty simple task. All you have to do is port your evaluation functions in Predibase, and then create a data set consisting of 10, 20, or 100 samples that has your prompts, and that prompts could contain the RAG stuff that you have extracted. So you have a pair of prompts, you have evaluation functions, and for each prompt you have what the ground truth answer should look like, right? So if you once you have all these things, then kicking off an RFT job in Predibase is a pretty straightforward thing. And once that happens, you can keep monitoring the output. Like we stream the model's output as the training is progressing to the UI, so you can verify what is going on with the model, whether it is correctly solving your task or not, right? So for me, the way I think of it is the biggest thing is setting up your evaluation functions. Then the second thing is how do you change your prompt? How do you change your input? How do you restructure the problem a little bit to do really well on that evaluation function? And in the process, also modify evaluation functions if necessary, right? And then move to RFT, where the final thing is just dumping everything in Predibase and letting it run.
Yeah, I agree that the most important thing is starting with good evaluations. Definitely when we talk to customers and they're stuck and they don't know how to progress, it's usually because they don't have a good internal sense of how well their baseline is doing today. Like if I'm using a proprietary model like OpenAI's, or if I'm using, like an off-the-shelf LM or something like that, how well, like what is the metric that you care about? Having a way of quantifying that, like with like a held out ground truth data set. And then once you have that very clear eval criteria, then the reward functions, at least the first version of those reward functions, is very straightforward, right? Because you use the exact same eval criteria to then create your reward functions. Now, that said, once you have the initial reward functions, you might still find as you progress like training, or if you run like kind of a quick sanity check where you take all your data, the baseline model, score it, what you might find is that there's not a lot of, coming back to this point of like variation between the different generations, right? Where like every time you prompt a model with particular input and you set the temperature to something, then you're going to get, the same answer. If that's the case, where you're not getting a lot of variation in the reward scores, that's where you want to start thinking about breaking the reward function down into partial credit, right? So being able to say, okay, it didn't get it right, but did it at least get something right that I can kind of directionally signal to the learning process, like this answer, even though both of them are wrong, this answer is actually better than this other answer. And if you can do that, you'll speed up the learning process pretty considerably. So there's some good kind of reference examples for this for different problem types. So for example, you might have like a structured generation problem, like a named entity recognition problem. Kind of the very straightforward V0 approach to the reward function could just be, here's the input, extract all the entities into a JSON object, and then if the JSON matches the ground truth, then it gets a score of 1, otherwise it gets a score of 0. That might work, but again, like if you're not getting a lot of variation, it might actually not work at all. So what you can do instead is you can assign partial credit based on how many fields or properties of the JSON object it gets right, right? So if you have like 10 different properties like name, email, address, whatever, and it gets like 7 out of 10 right, and then another one gets 4 out of 10, then you can give it reward scores like 0.7 and 0.4 to show it that there's like, answers that are more right than others, right? And it can help learn from that. Another example would be for classification, like one thing that some people have done, if it's like a multi-class classification problem, say you have like 10 different classes. What we've seen people do is instead of just asking the model to predict the right answer, it could say, sort the labels, the different classes into a list of like the most likely to least likely. And then ideally, the correct label is the first element in the list, like the most likely one. But then how far it is from being the first element in the list, it could be another way of assigning a score, right? So the further it is from like the top position, the lower score it is, right? So you can get a sense for like how confident the model is with an approach like that. So there are different ways that you can do it, but partial credit is very important. And I guess this does actually bring back one other important hyperparameter that we forgot to mention, which is temperature. So we mentioned it there is like, yeah, ultimately all this is driven by, temperature-based random sampling. So making sure that you're setting the temperature in such a way that for any given input, you're getting variations of different output, that also ends up being very important to making this whole process work.
Awesome. I love all the little tips and tricks about how to think about rewards. It's more than just a wrong or right. There's a lot of ways to do it to improve the output. There was a question in the Q&A about reward hacking. So there's been discussions online and people referencing it. What are like examples where this occurs, or how do you avoid it? Arnav, maybe you want to take this one. I know you spent a lot of time. Yeah.
Yeah, I can talk about like one use case that we worked on where we saw this and how we got around it, and then I'll try and think about like a more general framework for how to do it. So one of the first things that we sort of experimented with when GRPO first came out was this task of code transpilation. So given PyTorch code, can you have it automatically write like a Triton kernel to do the same operation correctly, but a lot faster on the GPUs? And what we found, as it was training was that, initially like the rewards are pretty low, but all of a sudden, right, you see a big spike in reward scores, fast, like much faster than you would normally expect, because rewards increase kind of more gradually. And when we looked at what the outputs were, and this is why observability is very important in the RL process, is that the model learned to basically write like a dummy kernel that does nothing, and thus invoke the torch function instead of the CUDA kernel. And it would invoke the same Python code, but just as like the last step in the function, so that the output would always be correct. And this happened like the result of this is basically it's a very smart sort of way to work around, where it's meeting all the constraints of a problem, like writing a kernel, but still finding ways to bypass doing the work of writing an accurate kernel. And the way we got around this, for example, was specifically writing mechanisms to detect this kind of cheating, and then basically giving it 0 rewards in those scenarios. So in this case, what we would do is we would write like a no-op kernel, which does nothing. And then we'd see the output of that versus like the kernel it generated and the output of that. And if those are the same, then we know that basically it wrote like a no-op kernel or a kernel that does no real work. So we get much lower rewards. And when we wrote this, we saw the rewards actually drop pretty dramatically. And then again, during the course of training, I slowly started to figure out how to actually write fairly accurate kernels. Now, this is one example where we saw it, we wrote a mechanism to fix it, and then we saw improvements. But in general, I think one big like trait that I've seen that suggests reward hacking is when you see very spiky values in rewards over a very short duration of training. It means that it's usually found a way to exploit something in the system very quickly, and that you're seeing like dramatic reward scores. So if you're doing like, let me think a good example, like, like agentic planning, where you're trying to plan, like, here are the 10 tools I have, but I need to use the subset of 5. It might learn that, hey, like, just by property of the data it's seeing, these 5 tools are hardly ever used. We always use these 5. So focus on these. And they might find ways to exploit that, which might be good, might be bad depending on your problem. But if it starts off really low, but then, yeah, you see big spikes in reward very quickly, it's usually a sign. The only exception to this rule, from what I've seen, is like formatting. I think format reward functions can be hacked, but it's not the worst thing when they are hacked, because you kind of actually want it to learn the formatting much faster than everything else, because then it can focus on that. Yeah, and I'd say like, yeah, observability is super key. You need to be able to see every generation for every step of training for every prompt, and be able to see that very quickly to catch these things.
By the way, are there other reward hacking is obviously like a landmine that comes up. Are there other sort of landmines that you guys see that maybe surprise you as you're training models, or things that people should be aware of to avoid, as things can be problematic when you're using RFT?
Mm.
If not, that's okay too. We have more questions, but I just
Yeah,
thought I would ask.
I'm thinking about anything
Yeah,
we have maybe have not discussed so far.
yeah.
One weird thing that I've seen, and it's happened extremely rarely, is that, reinforcement learning, the truth is that it's been in like research and academia for a while, like I think like the last 10 years in particular. But it is fairly unstable. And what I mean by unstable is that the models have tendencies to collapse from time to time. Um, and I'd say like, PPO historically is complicated because it's memory intensive and you have to do these reward models and value functions, but it can still collapse. And I'd say GRPO I've so far from what I've seen has less tendency to collapse, but it's still possible. It's like one of those things where you might have done everything right, and yet because of the sort of like dynamic online nature of the problem, it might still collapse because it decided to, let's say, reward hack and then go down a path that is really inefficient to problem solving. So the scores drop, and then it's not able to figure out a way to recover from that. Happens very often. Well, not very often, but like um, it can happen. I have seen it happen in like some cases. Um, I think there, like some of it is just the nature of the problem. So it's not to say the RFT can't work, more that it's maybe just a run and you might need to rerun it or resume it from like a different checkpoint. But I think like the formula to that is checkpoint frequently and often so that you have a state to recover from when things go sort of off the path of like stability. Um, yeah, and again, something that we try and do at least during our training runs within the platform, which is checkpoint very frequently so you can recover from any point if things go really like downhill.
Great. One question on evaluations. If your output isn't objective, and this is tied to rewards, how would you design a reward function using an LM as a judge? How do you think about that when it's not as objective?
Yeah. So there are some different ways that have been explored. I mean, this kind of gets back into the difference between RFT and RLHF, reinforcement learning from human feedback, where the goal is to align to subjective human preferences rather than to solve an objective like problem. But that said, there is some early exploration here. I think that in general, there's like a broad belief that like this is directionally going to be very valuable, and I expect that like we're going to see more and more research coming out in the coming months in this direction. But today, I think what I've seen, at least tried to, with varying degrees of success, is because of the kind of online nature of reinforcement learning and reinforcement fine-tuning, um, in order to kind of learn these more subjective tasks, you still need a way of like scoring it live, as the model is kind of producing dynamic outputs, right? So what you is probably not going to be practical is like just having a human there, subjectively judging every single output that comes out of the model, right? It's just not going to scale. But what you can do is have a separate model that's called a reward model that acts as somewhat of a proxy for the human's judgment. So, let's say you collect like 1,000 or so examples of like, here's an input, and then here's a human judgment of like good, bad, or like score between 0 and 1, or as in the DPO case, like preference pair data. Then what you can do is train a basic regression model, like a BERT model or something like that, that then learns from that data to, given any input, predict what the human who rated that original data set would say is, the quality of this output. Is it of this answer? Is it like good or bad, right? So basically, you would, feed as input to this model, like here was the input, the question, whatever. Here was the output that was generated from the model, and then the output is then score, like 0, 1, or whatever, right? And once you have this model, then you can run a kind of standard RFT process where you're creating input, you're feeding inputs in, it's generating like some number of different randomized generations for each input. And then you apply your reward model to each of those input output pairs, score them, and then those scores become rewards in kind of the normal RFT sense of having a reward function. And I think the quality of this obviously depends extremely heavily on the quality of that reward model, like how well it's actually acting as a proxy for the human judgment. But if the reward model correlates very strongly with the human preferences, then this process can actually work and can actually lead to the model aligning better to these subjective types of tasks.
Very cool. Cool approach to thinking. Cool way to think about rewards. Maybe for you, Arnav, real quick, because this one just came in chat as well. Since you worked on the Triton use case, is there anything you would change, or advise someone to change in terms of reward strategy and valuation functions if they were doing this not for like Triton, but for some of these other frameworks like Rockham,
Yeah,
V1 and others?
it's a great question. To be honest, like the only thing that you need to change is checking for reward hacking. Like I think the general principles remain the same. As far as I remember, we basically wrote uh, a few different reward functions. There was one for formatting so that the function itself is correct and follows like a structure that we want. The second one was compilation, like does the code compile without any errors? The third was correctness, which was done through test cases. So would definitely like recommend basically having test cases that would pass with an equivalent ROCM or HIP kernel. And then the fourth was speed. I think all four of those actually apply yet again for the ROCM side of things. I think the biggest thing is like writing code that will correctly check for reward hacking. Yeah, that's what I can think of. But yeah, curious, Travis, what you think?
Yeah, I mean, honestly, I think the biggest difference is just going to be not as much on the kind of algorithmic side, but just on the infrastructure side is that, Triton is a little bit simpler because, it's like ultimately Python just in time compiled. If you're running the reward server on a machine that has an NVIDIA GPU and CUDA, it's pretty easy to test it, within the reward server. But in the case of, something like Rockham, you would need to be running this on AMD hardware, and then you would have to have, some way of like executing the kernel, and comparing it to the outputs from the original CUDA test cases. And that's something where, you could maybe do like an offline step to generate the expected outputs for all the CUDA stuff, once, save that off somewhere so that you don't have to like run this process with like both an NVIDIA GPU and an AMD GPU. But then, in your like online training process, you'd be running your reward server on an AMD GPU. You would run the test, you'd compile, run the test cases, and then compare the outputs to like the saved outputs from the CUDA version, and then verify that like you're getting the same results. So the process would look very similar, but there would be some infrastructure changes that you would have to go through to make it work. In some ways, it should be easier from an algorithmic side because reward hacking is less likely in this approach, simply because I wouldn't expect that like the CUDA stuff like that would work as like a hacking strategy, right? To like do it in CUDA instead of ROCm on AMD hardware, right? It would just be a compiler error. So hopefully, should be less likely to run into that scenario.
Nice. I know we're just about the end, so maybe I'll just do one question of my own. Hot take or something you're most excited about with regards to RFT in the future. If each of you want to take a stab at it, what's something that you're getting excited about or a hot take about where it's going?
Yeah, I mean, for me, I think the two that are top of mind for me are RFT for agentic multi-step use cases. I think that's definitely one that increasingly you're seeing companies roll out these like elaborate kind of agentic workflows. And I think that as you want to think about improving these things, eventually you're going to want to have some diagnostics around like, okay, for this big multi-step process, where did things go wrong? And then how, and be able to annotate that in some way and flag it. And then the question is, after you've annotated all this information, like how do you then go and learn from it? And that's where I think RFT can play a really big part in the future is if, you have that observability, again, coming back to what Ajinkya said of like, for a complex system, like where is it breaking down? How well is it performing? And then you can translate that directly into reward functions. Then RFT can be the mechanism for this kind of self-improvement of like not just a single model, but like potentially a chain of multiple different models that are all working together. And so I think that's something that's very valuable. And I think that kind of goes hand in hand with this idea that was alluded to earlier of like learning from feedback and like not just being able to say, here's the right answer for this particular problem, but like here's but here's some feedback from either a human or from the environment, indicating like whether or not this was successful and be able to learn from that. And, a good example here, rather than just like human judgment, would be say you have like a big complicated agentic system that's trying to, I don't know, make like trades on your behalf for your stock portfolio or something, right? Like if you could ultimately, uh, like derive the whole end state of like, okay, how much money did this system actually make me or not? Like, am I gaining money or am I losing money? And then be able to back out from that, like some kind of reward model or policy, that could be very powerful, right? Because then it's not just like a matter of humans labeling, it's like connecting these things directly to the business metrics, like that actually matter, and then learning from those rather than having to have a data scientist or someone act as an intermediary between what actually matters to the business and what the model can understand in the learning process.
I like it, and I want that model. Um, Arnav and Ajinkya, any final thoughts on the future of things?
I had almost order like the same thoughts that Travis had, and I was like, okay, I will talk about this, and mentioned it. In general, like my hot take is that I think people have historically shied away from fine-tuning, either because of data or because of infrastructure complexity or just lack of understanding and knowledge. But I think that I already see like a big change in the kind of interest that people have and for the kinds of use cases that people have. And I think this will continue to be the case in the agentic world. Um, Sort of like a sidetrack, but similar track is that I think, people are having a lot of discussions around like agentic pricing, like do we price for like partial work or outcome-based rewards? And all of these tie in really, really strongly into this like paradigm of RFT, right? It's like if you're like, yeah, like, do you only charge for agents that finish outcomes or things like that? And I think because of like that push towards like those kinds of pricing models, like the only way to get your AI to be reliable to do that and make money as a business is going to be something like this. And so I think, yeah, basically I heard Alexander Wang also mention this recently at like a YC podcast, which is like models will be the IP, the environments for training will be the IP, and the eval harnesses will be the IP as well, that like you would never want to give away. And we're accelerating towards that future very quickly.
Nice. Ajinkya, any parting thoughts?
Yeah, so I'm gonna say this. If agentic workflows are going to be real, and then GRP is the only thing that you can make them successful with. And the simple problem with agentic workflows is 95% accuracy for a single step in isolation is great. Like if you give me a task and a model is able to solve it 95% of the time, that's amazing, right? But with agentic workflows, that 95% gets coupled with other multiple steps, right? And it's a cascade. So let's say you have 95% probability of one single step succeeding, and you have four steps downstream from that, right? And each has 90.95%. Then your cumulative chances of success are just 77%. That's that's horrible, right? So what it means is you can't have 95% accurate systems anymore. You need 99.999% accurate systems, right? And you're not gonna get there with bigger context, even bigger models. or SFT or like all of these techniques. You're like the final thing that you will always need is GRPO, like RFT or something, right? So I don't think sooner or later this is going to be the norm. That's my hot take.
Love it. And it's a very valuable point with agentic workflows being so hot. Hey, a big thank you to our AMA group here, and a big thank you to the audience for all the great questions. Hope you got enjoyed it. I certainly did, and we'll be doing more of these in the future. So thanks again, everybody, and have a great rest of your Friday. Catch you on the next one.